All right, so we're going to go over the solutions to the organic chemistry subject test A, which mostly deals with structure and bonding. So if we look at the first question, it asks us which of the following is true of benzene. So let's discuss some benzene basics, if you will. So benzene can be drawn several different ways. One of the more common ways is to draw a hexagon with alternating carbon-carbon double bonds and carbon-carbon single bonds. What you need to remember, however, is that resonance is in play because all these carbons are sp2 hybridized. So the pi bonds at one moment, and let me just number this ring as follows to give us a good reference point. Of course, remember with resonance we have the double-headed arrow. I'm going to use the same numbering scheme for this resonance structure. So the idea is that if we look at carbon 1 and carbon 2, half the time it's a carbon-carbon double bond, half the time it's a carbon-carbon single bond. So overall, these 6 pi electrons are delocalized over the entire surface of this ring, which means any carbon-carbon bond length is technically 1.5 bonds when you take the weighted average. If I look at C2, C3, in the first structure it's a single bond, but in the second structure it's a double bond. So it's 3 bonds over 2 resonance pictures. That's where we get the 1.5. That's 3 halves. So all of the bond lengths are equal. So all carbon-carbon bond lengths are equal. If we look at our answer choices, A and B are both incorrect. Half the time they're a single bond, half the time they're a double bond. But C is always going to be correct. All the carbon-carbon lengths in benzene are the same length. They are longer than a double bond, but shorter than a single bond. In fact, this is, of course, consistent with the notion that it's 1.5 bonds. Okay, next one we're going to look at is question 3. Which of the following is the correct structure of an acid anhydride? You get an acid anhydride when you get 2 carboxylic acids. I'm going to draw the structure of acetic acid just to keep it simple. So if I take 2 carboxylic acids, in this case 2 acetic acid molecules, and I perform a condensation reaction, I lose the elements of water. Notice I'm circling H2O. This is going to go away. And what I'm left with are these 2 acetyl groups that are linked together through an oxygen atom. This is an acid anhydride. So just so we can review functional groups, let's look at how we would term the functional group for A. A would be an ester. An ester we'll have an R group that's bonded to a carbonyl. So remember, that's a carbon-oxygen double bond. Then a carbon-oxygen single bond, and then an oxygen-R single bond. So that's an ester. B is a carboxylic acid. And so I have an R, C double bond O, then an OH. Of course, we've already decided that C is the acid anhydride. D is an amide. So I have an R, C double bond O, and then a CN single bond. It could be NH2, NHR, NR2. All of those would be consistent with an amide. Okay, for our next question, we're asked to identify the molecule that has the highest boiling point. I want to keep this very simple. Alcohols and carboxylic acids have the highest boiling points because they can hydrogen bond. Carboxylic acids have the highest boiling points of any organic functional group because they make very stable dimers. For example, this is a 1,5,6. This is hexanoic acid. And so I'm going to draw the structure of one hexanoic acid molecule. And then for the second one, and for this one I'm going to render it in red.
Sorry.
And I want you to notice you have two really significant hydrogen bonds. So one is between the carbonyl of the first molecule and the hydrogen of the hydroxyl of the second molecule. And then you have the same interaction, only it's the hydroxyl of the first molecule and the carbonyl of the second. So this is a dimer. And notice this dimer really looks like a six-membered ring, which we know are pretty stable in nature. So this is exceptionally stable. So if you ever have a carboxylic acid among the answer choices, I would always gravitate to that. You also want to make sure you're always comparing the same number of carbons so that the molecular weight is about the same. The more electrons you have, the higher the boiling point would be. For example, if I had acetic acid but I had octane, I would pick octane over acetic acid because octane has so many more carbons and hydrogens and thus so many more electrons. Here the number of carbons we have, if we look at all the answer choices, I have 6 carbons, I have 6 carbons, I have 6 carbons, I have 6 carbons. So we're making an equitable comparison, so then you go with the carboxylic acid functional group. Okay, the next question, ethene. We need to have a structure for ethene. C2H4. Just from the name, we need to suspect that we have a carbon-carbon double bond. And then each carbon, in order to make its 4 bonds, has a carbon-hydrogen, 2 carbon-hydrogen single bonds. Remember, a nice shortcut for determining hybridization of carbon is let's count the areas of electron density. This carbon has 3 areas of electron density. 1 area, 2 areas, and 3 areas. We can literally label these as S, P1, P2. That is sp2 hybridization. With sp2 hybridization, the bond angles are going to be very close, though not exactly, 120 degrees. So we can eliminate A and D because the hybridization isn't correct. And you can eliminate C because the bond angle listed as a bond angle for tetrahedral geometry, not for trigonal planar geometry. So this would be a trigonal planar geometry. Now that's not part of the answer choices, but it never hurts to emphasize this. Okay, next question. Which of the following is an amide? Remember, an amide, as we saw in a previous question, has an R group and a carbonyl, so C double bond O, and then a C single bond N. Now, the N is going to be bonded to two other things. They could be other carbons or they could be hydrogens. So let's look at each response individually. Number one, A is an amine. It's a carbon-nitrogen single bond. So, in fact, we would call this an aromatic or aryl amine. B would be an amide. Notice that our R group is an ethyl group, then a carbon-oxygen double bond, and a carbon-nitrogen single bond, which is exactly how we defined the functional group earlier. If we look at C, again, here we have an interesting molecule, but really it's a secondary amine. I have a carbon bonded to a nitrogen bonded to another carbon. So that would be a secondary amine. No carbonyl at all. And of course, D is an aryl nitro compound. Only B has the carbonyl. The carbonyl is an essential piece in the amide. So here's the amide part right here.
Oh.
If you don't have the carbonyl, you do not have an amide. All right, so the next question we're going to talk about is the order of boiling points for the following compounds. This is really a referendum on intermolecular forces. So we have propanoic acid, and earlier in this podcast discussed how carboxylic acids have the highest boiling points. We have N-propanol. And finally, we have ethyl methyl ether. This is simply going to be the carboxylic acid has a greater boiling point than the alcohol. The alcohol has a greater boiling point than the ether, because here you get more significant hydrogen bonds because of the dimer. Here you have hydrogen bonds. Here you do not. 1 is greater than 2 is greater than 3, which is answer choice B. Okay, so here we're given a pseudochemical reaction question where I have acetylene and I am going to react acetylene with 2 equivalents of diatomic hydrogen. So essentially what this does is it adds across 2 pi bonds. And so the first equivalent of H2, 1 H2 adds to each carbon, and then a second equivalent of H2 will also add to each carbon. Remember, this is syn addition. Remember that a carbon-carbon single bond is longer than, but weaker than, a carbon-carbon double bond, which is longer than, but weaker than, a carbon-carbon triple bond. In this problem, we are given a bond length for the carbon-carbon triple bond. It's 1.2 angstroms. I know that the carbon-carbon double bond would be longer than that, and I know that the carbon-carbon single bond would be even longer than that. You have to eliminate A and B because they're shorter. You're now left with 1.3 and 1.5. 1.5 is the best answer because if this were 1.3, it would leave very little room for the carbon-carbon double bond. So 1.5 is the best answer. What you definitely should be able to do is to eliminate A and B right off the bat. Next question, which of the following statements is true regarding the relative boiling points of cis and trans 1,2-dichloroethene? Let's draw those molecules quickly. So here's the cis. Of course, these other two substituents are hydrogen atoms. And of course, the trans and the hydrogens. If we start looking at dipole moments, when we look at the trans, the dipoles cancel because what is predominant in the dipole is the polarized carbon-chlorine bond. These are equal in magnitude, opposite in direction, 0 dBs. But here, they will not be 0. In fact, if I look at the overall dipole, it's going to be straight up. So this is a non-zero dipole. So if I'm looking at IMF, I've got to look at dipole moment in terms of IMF. The IMF should be greater with the cis compound as compared to the trans because I have a dipole with the cis and not with the trans, which means the boiling point of the cis should be greater than the boiling point of the trans because it has a net dipole moment, which means it has more significant intermolecular forces. Now, remember when you start talking about boiling points, IMF is the key descriptor. You can't pick B because it has nothing to do with thermodynamic stability. You can't pick C because it has nothing to do with delocalization. And you can't pick D because it isn't more symmetrical. The cis compound is more symmetrical. In fact, if you look at this through another lens, here the left side is the mirror image of the right side. So A and C and D are not even correct answers. A is not only correct, it explains the difference. So A is the best answer here. All right, on this question we're asked, which of the following is the most stable carbocation? I want to draw each of these structures and then we'll discuss them in more detail. So the first one is simply a vinyl carbocation. The second one is what we call an allylic carbocation. The third one is a primary carbocation. And the fourth one is also a primary carbocation. Now, there are two driving forces for stability of carbocations. One is the inductive effect. The inductive effect is a consequence of orbital overlap with the empty p orbital that results from the carbocations sp2 hybridization. From the inductive effect and hyperconjugation, we say that tertiary carbocations are more stable than secondary carbocations, which are significantly more stable than primary carbocations, which are significantly more stable than methyl carbocations. The other driving force is resonance. Benzylic is more stable than allylic, which is significantly more stable than either phenylic or vinylic. The resonance effect in almost every case in organic chemistry trumps the inductive effect. That makes B the best answer. I have a resonance stabilized carbocation. I do not have resonance stabilization here because the positive charge is 2 carbons away from pi density. This is an sp3 hybridized atom. It is a resonance breaker. This is a primary carbocation. This is a vinylic carbocation. It's not even close. B is by far and away the best answer choice. 2 driving forces, induction effect and resonance trumps the inductive effect.